So there's a new tutorial for this week for today, and there's a lab this afternoon. I'm going to give a review on quiz 2 and quiz 3 really quick. And the week after next week, on Tuesday, there will be a quiz 4 on shift register, and on Thursday, there will be a quiz on sequential circuit design. So these 2 quizzes are based off whatever we're going to cover today. So please pay some attention to these 2 materials, the 2 parts of it. Okay, I think before we dive into this, I'm going to run the quiz review really quick. Just give you guys some feedback on that. But surprisingly, the first one, you guys didn't do that really well. It's probably too simple, so you didn't pay too much attention to it. But made a lot of mistakes over there. So the questions are just 2 very simple numbers in the decimal form. So if you're trying to find the floating point representations, you have to convert it to the S, E, and F. So then you combine them together to make up that floating point representation. So for A, you want to write down the number first, right? And you should know that X equals SEF. So E and 5.25 equals what? It's going to be 101.01, right? And this equals 1.0101 times 2 to the second power. So E equals 15, which is the offside, plus 2, which is 17. So 17 is basically 10001. So you need 3 zeros in the middle. A lot of you guys just put 2 zeros in the middle, so lost some points over there. So what is F? F is going to be these 4 digits. Just directly write it down. And because you know that F has 10 bits over there, so I have to make up 6 trillion zeros after that. So X eventually equals SEF, which is because the sign bit is definitely 0. And then directly write down E here, 10001, and then F, 0101 and 6 zeros. And eventually the format should be the hex format. So group the 4 digits into 1 hex digit. Start getting these. This is 4. Is that 5? 40, right? So 0x4540 is for the floating point representation for this number. And again, the similar thing, just follow the certain steps over here for the second one, right? Are similar. And for the second problem on the quiz, it's an odd parity bit generator, and it's a 2-bit. The data length is 2-bit, and adding 1 more parity bit, you're getting 3 bits overall. But you're considering the data bits are AB, for example, that's a parity bit. All the combinations are, the possible combinations are 0001, 1011. And you want to make it odd number of ones. You need to add a 1 here to make a odd number of ones for the first one. And 0, 0, 1, like that. So from the truth table, you can find the logic equations from it, which is P equals A not B not or AB. And almost every one of you treated this one as XOR. It's not XOR, it's XNOR. So this is A, so XNOR B, which is A XOR B not. Okay, So what's the gate symbol for XNOR? So it's XOR, right? This is XOR. And I add a little bubble there. A, B, P. Okay, you can also do this. It's going to generate the same result. Got 20 points if you do either one of them, but you have to make the logic correct first. So in Verilog, you all know how to do XOR, because XNOR is the inverted version of XOR, so just add a little inverter in front of it to generate a P, right? Just assign this to P in Verilog. But in the quiz, you want to write down the ports, the module, and module, and all the kind of things, right? Input, output. That's clear on the quiz? Okay. Any questions so far? No, simple. So we may see the similar problems in the midterm because you didn't. Not too many of you are getting full score on this quiz. It's good to test you guys one more time in the midterm. And quiz 3 is due next Tuesday, right? So you want to post your code, your video demonstration and explanation exactly on that day at 11:15 a.m. or a few minutes later, which is fine. Just you just have everything uploaded to the server, and then you just add the link to the report, right? At the moment, just make it activated. Just activate that link on the server at that time point. It's not asking you to get everything uploaded to it and then activate the link. It takes a lot of time, but you get everything ready, just activate the link. Only takes a few seconds. If you think about the process of the operation on the board, it's a push button triggered counter. There are 5 push buttons. You're only using 2 of them. It could be any 2 of them. And initially it shows a 0 on it. If you press one of them, you'll start the counter. And you press another one, it resets the counter. It cycles from 0 to 9 and back and forth. So when you are working on this kind of problem, what's the starting point of the design process? Where do you want to start with? Will make the things easier instead of thinking about the code and thinking about the circuit and everything else. It's just making it pretty messy. But is there a way to better organize the design process? You can exactly follow that process every time. This is a super simple quiz. What about the more complicated ones in the future? In multiple states. This one just have a 0 state and counting state, just 2 states. What about you have like 10 states or multiple inputs in different states to trigger different results? It can be more difficult. But just based on this simple problem, for example, just 2 states. So where did you start? What's the first step you want to do at the very beginning? Could any of you share your ideas?
I made the SSD count up
Yeah.
first. That was my first step.
Okay.
Just like making it count up every half second.
Mm-hmm.
And then worrying about triggering it.
So that's a counter module?
Yeah.
Okay. Did you put a counter module in something else, or is it just a counter module itself?
I just incorporated it all together.
Oh, okay.
In one module.
Yeah.
But that was like what I started, uploaded it, made sure that worked, and then went back and changed it.
Okay.
I did the same.
You do the same?
Yeah.
Same?
I built it from inside out. Started with the counting and then working to reset and start looking.
Mm-hmm. Do you think about the individual modules, or you just everything putting together?
I have this.
Okay, cool. So later on down the road, we are going to design some controllers for VGA, for SPI. They have at least 4 states at least, and a lot of times more than probably 5 or 6 different digital blocks in the circuit, and there are like over 10 or 20 wires in there. So I think it's better to draw the circuit diagram with individual blocks and interconnect them by just drawing on the paper and then just code up every single module by itself, and then eventually put them together in your test bench. We'll organize all the parts more clearly.
And I figured out that thing we were looking at in the office yesterday with the connecting.
Yeah.
You can either use a wire or you can call it output.
Got you.
Directly.
Okay, yeah, cool.
Well, I tested both ways. They both worked.
All worked? Yeah. Did you make it work eventually?
I'm like
close.
98% of the way.
Okay, cool. Good to know. So what I did at the very beginning was, since I know I'm going to use a debounce module to get a clear signal out, okay, and there will be two debounce modules because every debounce module serves one push button. And here's your because if you look at the debounce modules Verilog, they are both clocked. So you need a clock for it. So the clock is basically the clock from the board, and you divide it into a slower clock. And that's the push buttons connection. That's button C. Button C is the center button. Or you can use the button U, which is the upper button over there, or the button D, which is the one over here below the center one. And this one will create a clear button signal. Okay, and that one will change the state. So what I did is, it's not the most concise version, but will make things super simple. I didn't put the state machine in the counter. I just have an individual module of it. So that push the rising edge is going to change the state permanently. So it's not going to change back or something. It's just a one individual module here has an input and output. So it's taking the button clear input as the trigger signal and eventually assert the output to 1 permanently. And there will be a counter is accepting the state signal. So the counter is definitely clocked. And also there's a reset because it's receiving the other button's output, and the counter will be reset to 0, okay? And the counter is outputting a certain length of output, and this is determined by all the digits because I'm trying to display 0 to 9, right? So I just need 4 bits, which is able to show 16. If I only have 3 bits, then I won't be able to cycle through all the numbers, right? It's only, so I have 10 numbers here, so I need 16 different combinations. And I have another one, which is the display. It receives all the numbers and convert it to the G to A display directly interface with the SSD. So this will be an interface here as well, which is a 4-bit line. So if you see all these individual modules will be included in the test bench eventually. And you have to add pieces of wires. So this wire is a 4-bit wire. And you need a wire here as well to interconnect all the different modules. And whenever this state is 1, so in your counters logic, it's going to be if state is 1. Okay, that's the overall condition. If state is 1, you do all the following, okay, including the counter equals the count max, then do something, right? Or cycle, if it's 9, then reset to 0. If it's not 9, then keep adding 1 to it, right? It all depends on this input. So there's a little state machine. It's a very simple state machine because on only 2 states, either displaying on 0 or you get this push button pushed, and it's going to trigger the state to be changed to 1 instead of 0. Okay. So that's the state controller, right? And it's providing a state signal to all the following circuits. And so if you draw this diagram, It's going to be very clear about all the name of the wires, and when you're programming the test bench, you just put them, include all the individual modules and put the wires in there and do the interconnections. And I think this can be done probably in 1 or 2 hours, including the synthesis and coding. So we're going to have 1, 2, 3, 4, because this is the equivalent module. You have 4 modules, including the test bench, to make 5 modules. There must be different ways to do it, but I think this just organize all those components really clearly is not putting things into somewhere, right?
If we already have it done a different way,
yeah,
do we need to change it
to
be this way?
Definitely not. Yeah,
okay.
yeah.
I'm scared.
Yeah. Okay. If you haven't done that yet, this could be a reference, serving as a reference. So sequential circuit design. I think this is pretty important. Teaches you how to convert a sequential circuit into a into Verilog, or from the state table into Verilog. Depends on what is available at the moment. So I don't know if you still remember how to convert this one to a truth table. The reason you need the truth table is only from the truth table you can find out. Only from the logic expression you can start from here to write all the Verilog. Because our brain works that way. You cannot directly code up Verilog from the sequential circuit. It's very difficult, right? How to do that. Data flow version, but you have D flip-flops, right? It could be challenging. Okay. So if you have a sequential circuit like that, it's a D flip-flop. So whenever there's a rising edge, it's triggering the D flip-flop and sending this data to here. Okay, that's how that works. There's the input and also 2 state holders. It's just how many bits in the state variable. How many bits are in there? I think. So what are these 2 D flip-flops doing in the sequential circuit? What are they? So they are just the state holders. They're holding that specific state at the moment. And because you have 2 D flip-flops, so the length of the state variable will be 2 bits. Okay, you have 0, 0, 0, 1, 1, 0, 1, 1. You have eventually 4 states that you can use. And that's the input. So the input will change the state, but it also depends on the previous state. I mean, so the sequential circuit is a little different from the combinational ones. So the output Y depends on the input and also the current state of the state machine. So the question here is, because this one, after the clock rising edge, this data here will be sent to Q, right, as output. So which one, when you are writing down the logic equation from this circuit, you can see Qn is the current state and Qn plus 1 is the next state. So is this Qn or is this Qn? Which one is Qn? Which one is Qn plus 1? Which is the current Q? Which is the current state? Which is the next state?
Is Q2 the next?
It's actually, the data here will be the next state because the rising edge arrives, this will be Q2. So that's why D is actually the next state, it's Q plus 1, Qn plus 1, but the current data is actually at Q. Why? Because this data is not being controlled. It's directly going through all the gates and contributing to Y, right? It's a current state. But whenever the rising edge arrives, it's gonna apply all these variables and send whatever at D to Q, which becomes the next state. So the next state means after the rising edge of the clock, what the Q is. So that Q will be the next state. If a sequential circuit like this is given, it could be an engineering problem in the company or wherever, could be any applications. If you know the sequential circuit like that, from anywhere, okay, the customer probably gave you this circuit and lets you code it up in Verilog and implement exactly the same logic over here. You know how to code up a computational logic just using all the operators for the simple XOR or AND, right? Just do it. Very simple. What about the sequential circuit like that? It's just something on the paper, right? It's something on the paper. People provide it. The customer provided to the company and letting the RD people in the company to implement it on the chip. This is a schematic on the paper. What's the way to convert it into FPGA? And we're not talking about putting the individual, the discrete IC chips on the breadboard and build it up, right? You do have a D flip-flop. You can find a D flip-flop from the drawer, and you're getting the NAND gates, OR gates, and D flip-flops, and you can wire it up. Just looking at schematic and put on the breadboard, it works. But we are talking about Verilog and FPGA.
Can you do that in Verilog with the gate logic? Figure out the behavior and then code it up?
It could be challenging because you have to incorporate the D flip-flop in there. How to do that? I mean,
You could make a truth table.
Yeah.
And then do like the Boolean algebra and then simplify it down into an expression.
Yeah. So you like expression, right? So eventually you can convert logic equations to Verilog. That's what we can do. And also you can simplify it that way. So when you convert it down from truth table to logic equations, there are multiple ways to simplify it. So eventually, when you look at the logic equation here, you don't even know what the circuit is. But if you implement this into Verilog, eventually it's going to work the same logic of whatever the schematic does. Actually, from the circuit to logic equations, we don't even have to put a truth table in there if you don't have to simplify it. We can directly, because we know this is Qn, right? And this is Qn plus 1. And you know what Qn plus 1 is because Q2n plus 1 equals all these kind of logic, which is directly shown on the schematic, right? Because this is Qn, right? Let's look at Qn plus 1. So Qn plus 1 is over here, right? So Qn and this guy, which is Q1n naught. So it's going to be Qn and Q1n naught. Or these three inputs ANDed, right? So it's going to be Q2n naught. And I'm going to ask you, what is this signal here? What is this signal? Because this is one of the inputs to the three input AND gate. So what is this signal? You want to put in the logic equation. Q1 what? So what is this one? Let's pick up a simple, easy one first. What is this one? Here. What is that? X. Okay. So what is this?
Q1.
Q1 what? Yeah, in Verilog it's just Q1, but what is Q1? Q1n. That's the current state. What is this one? Q2n naught. Okay. So just write up these three signals and AND it. Okay. And you got this output. So what is this?
Q1 naught.
Q1n naught. What is this? Q2n, right? And AND it. So got two outputs and OR it. And that becomes what? Q2n plus 1. So that's exactly what this logic equation is. Right? We just did it. Same to the next one. So Q1n naught, Q1n plus 1 will be this line. I can definitely find out what that signal is from the logic, from the schematic. All right, so from here to Verilog, it's very simple. Our brain can definitely work out. It's easy. So my question is, when you are writing up the Verilog code, you can use a Q to represent the state, just one bit, digital line in the circuit. So not, you know the operator to invert it, right? It's pretty simple. So what about Q2n plus 1 and Q2? What's the difference in Verilog? Are they two variables or just one?
One variable.
One variable. What's happening there? It's just updating itself.
So when you're doing the logic equations from a circuit like that, can you just do like D equals, what was it, Q2n plus 1?
Well, we don't need D at all. Why do we put D there?
I know, I'm saying like in the process of converting, like would it be maybe helpful to have like write out the equation with D and then have D as like, is that correct?
I think you can do it, but eventually you are assigning D to Q, right? Or just to use D as the next state, but have to assign D to Q itself because just a one signal. It should be one variable
so there's
here.
Like a D, there should be like a D1 and a D2, should be there?
Yeah.
Okay.
Then it's gonna be the same code, I think. No difference.
It will be the same code.
Yeah.
I'm just saying, like,
Sure.
That's a viable way to think
Yeah.
out. Okay.
That's right. Yeah. And in Verilog, because you have Q here, right? So Q and Qn plus 1, Qn will be the same variable, and you are having Qn, Q2n here as well. So what's going to happen is you're having Q2n here and Q2n here, and you're having multiple lines of code in Verilog. So should they be non-blocking or blocking assignment in Verilog? Do you want to block it before you finish the first line, or you want a non-blocking?
Should be non-blocking.
Should be non-blocking. Why?
Because it relies on the past input.
Relies on or not rely on? Oh, it's relying on past, but not the current.
Yes.
Right? So you want to use non-blocking because everything will be sent to here at the same time. You don't want to use the updated Q2 as a Q2 here. You know what I mean? That's a Q2, right? You got a Q2 here, and Q2 here. They are all Q2s. If you use blocking, whatever Q2 here is being used will be the updated Q2 instead of the old one. You don't want to use the old one. This should be the new one. It should be the old one. You don't want to use the new one.
So
is that clear? Okay.
Q2n plus 1, Q1n plus 1, like those assignments in Verilog would be run at the exact same time?
Yes.
Okay.
Based on the circuit, that's what the circuit tells you to do, right?
Yeah.
Yeah.
And then Y would also be blocked with that?
Why would what?
Y would be executed at the same time?
Because
The
if you
assignment
don't do that, the Q2 here will be the updated Q2.
Yeah.
Which is not really what the circuit tells you to do. Right? It's all the current Q2 doing all the jobs. Because on the right hand side of the D flip-flop, it's just a combinational logic. There's no, you're not using the next, you're using the current. Okay.
So then would Y be included? Like
yeah,
Y have to be executed at the same time as
yes.
Q2 and Q1?
Yeah, because Y is using the current queues instead of the next queues.
Okay.
Right. Clear? Okay. If you have the truth table, you can also, you may have to start with the truth table. You have the truth table. The next would be convert the truth table in the logic equations, and then you can convert it back to a sequential circuit or convert it to a Verilog. So depends on what you have, and eventually, if you want to work with Verilog to implement all the logic, you'll probably want to convert everything to the logic equation first. Okay. There are more examples over here. It's basically the same problem. And there's an example of the Verilog code to implement that sequential circuit. You can see I was trying to go through all the combinations of the states, trying to use a for loop. So eventually, this is not a really legit way to, simulate or verify the entire logic, or all the inputs, possible inputs for the logic equation. But they are able to verify part of it. So you can see I marked in red. So these are the states and transitions being verified in there. Okay. And that's the simulation results of it. And instead of using that logic equation, you can also, if you have a state table like that, or state machine diagram like this, you can also code it up using Verilog, right? But just using this is called the behavioral form. For example, if x is 0, you can look at all the inputs. So there's an inputs slash output. So that's x slash y. And that's the state. So you number the state as 0, 0, 0, 1, 1, 0, 1, 1. You have 4 states over there. So in Verilog, it's pretty simple. You just have the different states held in a variable called state. Okay, it's a 2-bit variable. If you look at here, it's from 1 to 0. It's a 2-bit variable. So if x is 0, it's all based on the from the diagram. You can see when x is 0. When x is 0, you can see this is x, 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 okay, or the bunch of x. So when x is 0, then you look in the state. If state is A, B, C, D, so these are A, B, C, Ds, right? If the state is A and the input is 0, it's actually jumping back to itself. Okay, so you want to assign A back to state. It's not changing the state. If the state is B, well, x 0, state B, and x 0 is jumping back to A. It's from this transition. So that's why I put an A to state. It's going to be the same, exactly the same strategy to code up all the state transitions. And then if x is not 0, if x is 1, and state is D, then assign 1 to Y. So it's basically just to look at all the transitions and states in the diagram and just code it up. No brainer. You don't have to simplify anything. Just to code it up in this form. It also works. Okay. So this is example. I'm not showing everything of it, so you need to finish it and run the simulation. Okay, here's a shift register. You have 4 different types of shift registers. Serial in, serial out. So which is just a one line of data input. How many of you have used UART in the past? UART, just serial communication. Yeah, for most of you, but yeah. So it's just a one line of input. Why do we want a serial? But in the past, most of the time it's just a parallel, digital parallel input. And there's a certain disadvantage of using that form of communication port. It's taking a lot of ping resources on the board. Okay, for example, here's a microcontroller unit. And there are different types of input lines. If you have a UART, it's a RX pin is receiving data just from one pin. But you are able to transmit 8-bit data packages to it, right? So eventually what's happening is you have a clock to trigger every single bit into this microcontroller, and there will be a shift register, right? And this input will inject that line into the first shift register. But what's happening inside the MCU is still parallel, okay? What that means is you got every single bit, for example, like this, okay? So this becomes 0, 1, 1, 1, 1, 0, okay? That's the digital data input. And I want to clock every single bit into this line, into this data line. It's just a 1-bit line into this shift register. So these bits will be put into the shift register, become 0, 1, 1, 1, 0, being stored in the shift register. And when it's ready, all these 6 lines, 6 digits will be pumped into another data processing. Could be a DAC, it's a digital to analog converter. It's a digital signal in and analog out, analog voltage out, for example, inside the chip easily. So my question here for you guys is, why do we prefer a serial in, parallel out in this specific situation? Why not just have a 6-bit input? Just faster. You don't have to wait for 6 clock cycles, right? It has to be clocked for 6 times in order to fill up all the memory. Have to shift it from here to here to get all the data ready in the memory bank, and then you use another clock cycle to send them out to the DAC for internal processing for certain applications. Why not just use 6 parallel bits? So just need a 1 clock cycle, okay, and all the bits will be sent to here. If this is the DAC, you can directly receive all the 6 bits in parallel at the same time to save the time, right? Then you don't have to wait for 6 clock cycles to receive all the 6 bits. You can just use 1 clock cycle. It's going to trigger all the D flip-flops and send all the bits to the DAC at the same time, just 1 clock cycle. Why we prefer this instead of this? This is slower. This is definitely slower, right? You have to wait for 6 cycles. This is just a 1 cycle. So the chip is receiving all the 6 bits at the same time. What's the reason for, almost every unit or every system on chip or microcontroller is doing serial instead of parallel? Nope.
So you can change individual bits without updating the whole thing?
Mm-mm.
It's just smaller.
Mm-hmm. Why is smaller? Because it's taking less number of pins. You have to know that on the integrated circuit design, the pin resources are super expensive. And just a simple 6-bit application, you are taking 6 pins, and even a lot of chip packages only have like 28 pins. And you want to do DAC, ADC, you want to do a lot of things, serials, HPI, I2C, and USB, and there's so many different things. You don't want to just use a one communication, a purpose or chip, take 6 bits. So this is just a 6-bit. If you want to improve the resolution of the communication, a lot of times it's like taking 12 pins. It's 12-bit resolution. And for the CPU in the desktop, do you know how many bits are in the computer system over here? Yeah, it's 64 bits. Can you imagine, like, only for one data transmission, you are getting 64 number of pins on the chip, connected to the chip. You probably only have like 100 pins for the CPU, the ones, the i7 or something from Intel, right? They don't have that many pins. You have a very limited area of the chip. So you want to use serial if you can, instead of using parallels. It's taking less pin resources. It's actually taking more power. It's every time you clock like 6 times, you have 64 bits. You have to clock 64 times to get all the bits ready in the memory bank of the chip. So another question here is why we don't care about the parallel pins inside the chip. And eventually they are parallel, right? You have to do parallel eventually. Why we don't care about whatever happening inside, we only care about the outside. That's right, yeah. So if you think about the most recent technologies being used for the foundries, the most updated, the most latest one for the CPUs used for the Snapdragon, for the Qualcomm's chips for the Samsung phones, or A10 something for the Apple phones, they are at like 5 nanometer technology, which means the smallest node they can make on the chip is 5 nanometers. You don't really care about how many lines you have. You can have like 1,000 lines in the chip. in parallel if you can process the data faster. So you really want the serial input or serial communication just at the pin level or the package level. But whenever you get into the chip, you want to do parallel whenever you can, because that's faster. So you can process all the data, like 64 bits of lines at the same time. You can directly send it to a certain, from the memory to a CPU and process it very quickly. Because the lines can be nanometer level. The pins, they have to be visible at least. If they have to solder them manually, sometimes use a machine, but they still have to be visible. Right? But these nanowires into the chip are most of the time are not visible by the naked eye. You couldn't see them unless you use a SEM, probably. So that's the idea of using shift registers. So this is serial in, parallel out. But you do have all other different types of shift registers. Could be parallel in, parallel out, parallel in, serial out, or serial in, serial out. Depends on how you want to use it. So in this tutorial, I showed you all the structures of the shift registers, and also showed you how to program it in Verilog. So what's the easiest one to program, you think, in Verilog? What's the easiest one to program? So serial in, serial out is basically a shift register. You shift all the data in to a line of different flops and shift them out. So just a one input, one output. And serial in, parallel out is whatever we just drew on the paper. It's one line in, and whenever the 4 bits are ready, you send them out at the same time. You get 4 parallel pins out. Okay? Or parallel in, parallel out. You got 4 bits in and different flop. When the clock arrives, you send them out directly. You're not doing anything to the data. So parallel in, serial out, which is you got a parallel in data and serial data out. So I just talked about the serial in, parallel out on the paper. And where are we going to use parallel in, serial out? Can you imagine? Why we need this, or where are we going to use it? We use the same principle, okay? Where are we going to use? One quick question. So what is a shift register here? What's the name of the shift register here?
Serial in, parallel out.
Okay. So in the DAC, you may need another shift register because it's taking in parallel input and doing a one line output. So why do you need just a one output for the DAC? What is the DAC? Digital to analog converter. So it's taking a digital input and convert it to analog output. So analog voltages are just a decimal number. Could be 5 volts, 3 volts, 2.5 volts, whatever. Okay, just a one analog voltage. Right? That's a DAC. What about it's not a DAC, it's something else? It could be a serial output. Serial output. So why do we need this instead of parallel in, parallel out? Same reason. You want to save the number of pins on the chip. So it could have digital input, that's a digital input. Also, it may have digital output. Okay. So for digital output, it's a TX for UART. It's a serial monitor you see on the Arduino chip. You have used Arduinos in M&I, right? So that's the UART, transmission communication. We just didn't use it down to the bottom level, but it's a USB to serial converter. The serial communication TX and RX converted to USB signals from the little black chip on the board, and then sent to the computer. You can see all the data from the serial monitor. That's why it's called a serial monitor, because it's using a serial communication. The same reason is taking parallel in and serial out. So this is P in SI, SO, right? Parallel in, serial out. Same reason. You only use too many pins on the chip. It's very expensive. Okay, let's come back to this question, okay? So which one is the easiest to program in Verilog?
Probably serial and serial.
Mm-mm. Mm-mm. No, parallel in, parallel out. It's basically just an assignment, just one line. This equals that. Just whenever clock arrives, right? Q in equals Q out. Just one line. So for the serial in parallel, I have to shift all the registers, shift all the bits. For example, if we take a look at the serial in, serial out, okay, you need like 4 lines, right? It has to be non-blocking. Has to be non-blocking. You don't want to wait an updated Q3. It's sending the current Q3, not the updated Q3 to the next. Keep in mind. Okay, that's serial in, serial out. Keep in mind the quiz problem. I'm going to ask you guys to write the Verilog code for a serial in, serial out shift register, right? Or serial in, parallel out, or parallel in. I'm not going to ask you to do a parallel in, parallel out. Take a look at it. That's okay. Parallel in, parallel out. Yeah, that's it. For whoever is not here today, will fail. So this is you need another load command for the parallel in and parallel out. Oh, sorry, it's a parallel in, serial out. You can see it's SO, it's a serial out. You need a load command, which is another level of control of D flip-flops. You have a parallel input, the P3, P2, P1, P0, right? So the parallel input. Okay, you have to load it. So the loading signal could be a clock signal, is a rising edge, and you load all the Ds to the input of D flip-flops. Okay, so they are sitting there, and then whenever the rising edge of the clock arrives, it's going to shift all the loaded data to the right. So the parallel in, serial out, you need a loading level here of the D flip-flops for another level of control for it. Okay. You see how to provide a clock for the simulation? It's pretty simple. Just always do it. It's always delay for 5 seconds and flip and toggle the clock. That's how you do it easily in your test bench to provide a clock signal for the simulation. Right. So most of the work in this tutorial is just a simulation, not really on the FPGA board. Counters, basically just a sequential circuit. Okay, if you give a signal in, it jumps to the next state, which is adding a 1 to it. And there's a counter example from the textbook. So the author is actually Turkish. Did you realize that? No? But he made a typo here. There's a typo. It has to be Y, Q instead of directly putting Q. It's gonna, have a synthesis error. So I have to correct it. Okay, you have to revise it like this: Y, Q plus 1. So the tasks. There are 3 or 4 for the first 5 ones. And what about the last one? Find the logic equation for the following circuit and implement it in Verilog and show the simulation results. Okay. as what we talked about in the just previously. The final purpose is to simulate in Verilog, convert into Verilog. Okay. So what's the next step? If you see a sequential circuit like that, what's the next step? Or where do you want to start with? So first, when you are writing the test bench, you have to be aware of that. You have a bubble here, which means it's a negative edge triggered. So it's always at negative edge of clock, then do something, right? So that's Z, and this is Qn, right? And this is Qn plus 1. All right. And then just do whatever we just covered at the beginning of the lecture. Write down the logic equations and convert the logic equation into a Verilog script and write the test bench for it and run the simulations. Okay. The lab. This could be done within a week, but you know, you probably have to take the time to do the quiz 3 and homework as well on the website. So I'm going to give you 2 weeks to work on this lab. And I'm not going to have a lecture this afternoon, so you can come to the lab. You can physically be there. If you have questions, I can help you out. Otherwise, you can do it wherever you want. You don't have to come to the lab. I find out a lot of you guys probably can do the job better when you're at home. It's more comfortable, or have snacks and all the others and coffee. Maybe your dog as well be next to you. So the traffic light control is actually just the 6 inputs, 6 outputs. So you can connect the 6 lights to 6 LEDs. Basically, our LED lights on the board doesn't have a color. But imagine, just 3 of them are like green, yellow, red, green, yellow, red. Just organize it that way. And these are outputs. So the input is going to be a clock cycle, and you have to divide it and make it slower. You have to give them some time to drive through, right? Not cycle through all the lights at 100 megahertz. No one can cross the street. So you want to make a reasonable frequency, divide the original clock from 100 megahertz to something, right? And so the states of the lights are cycling through all the different states: red, green, red, yellow, red, red, okay? And then green, red, yellow, red, okay? You have to put everything in the truth table and convert the truth table into logic equations. And from logic equations, you can directly write a Verilog code based on that and run the simulation and implement on the board to cycle through all the light transitions on the board. So that's problem number 1. The problem number 2, so I might ask you guys to change the, okay, so so for example, on this is a main street, okay? So during the rush hours, there will be a heavier traffic on this street. So to keep the green light longer, instead of this drive, okay, it's a smaller street. So in that way, you just modify the code, and to trigger a rush hour mode, it could be a switch. You turn on the switch, it triggers that rush hour mode. So in that mode, one direction of the of the traffic light, so one of the 2 traffic lights will keep the green light on for a longer time. Okay. It should be a pretty easy modification to the code and to implement that. Very simple. Any questions on this? The lab and anything else moving forward to the next week? You have any questions? No? Okay, if you look at the quizzes, it will be, it's gonna be, so probably prepare for the quiz the Tuesday after next week, shift registers. It's pretty simple, and on Thursday will be a sequential circuit design. It could be diagram to Verilog or Verilog to circuit diagram. I don't know yet. I don't have it yet. Just based on my creativity. See, on the airplane, I probably will think about it. How I want to test you guys on that. It will be reasonable. Any questions? So my laptop is running out of battery here, so I have to end it. All right, so you guys can start working on your stuff or go home to work on the tutorials or do whatever you want. Okay, so this afternoon, because you guys are all using your laptop, right? So I probably will stay in my office and you can work on the lab problems anywhere you want. But I will be in my office to help you guys out. Okay, so there won't be a lecture for the lab this afternoon. I'm gonna probably just go to Walmart to buy the bucket for you now.
Okay. The bucket.
Okay, yeah.
Cool. Lincoln's here, and he has a lot more experience with CAD design, and so I'm going to talk to him about making a bracket.
Nice. Yeah, perfect.